Hello and welcome everyone. My name is Boris Lange with Advent Optics, and I apologize for not being there in person at OPD in Tampere at this point in time. My flight was cancelled, so I'm sitting here at home right now. It's late at night and I will record the presentation, hoping that this video will get to you one way or the other. Again, my dearest apologies to the organizers and also to you. But let's cut this short. I'll just start sharing my screen and then let's talk about liquid lenses for a couple of minutes, because this is what my presentation is about. All right. So liquid lenses in machine vision are essentially just there to electronically adjust the working distance to whatever you need it to be. For example, in logistics, this is very common, where you have a conveyor belt, lots of packages traveling along, and you just focus on different working distance very quickly, very easily, electronically. And it has certain benefits over the alternatives, which would be motorized systems or using F numbers, very slow F numbers, and all of that, and all this kind of techniques that are out there as well. So let's get a little bit into the details here. I would like to talk about the two different technologies that are out there when it comes to liquid lenses. The first one is based on an effect called electrowetting, and this is utilized by a French company called Varioptic. They've been acquired by Corning, so today it's Corning Varioptic. And then the second concept is a slightly different approach, and this is used by a company, Optitune, based in Switzerland. Just to be clear, Advent Optics doesn't design and manufacture liquid lenses at all, but we sure do utilize them. We work with both of those companies and we implement their product into imaging systems, right? Because those liquid lenses by themselves are just a single element, so you cannot really use it to do imaging. But you can certainly integrate liquid lenses in imaging optics, and this is where Advent Optics comes into play. But let's start step by step, and we will kick things off talking a little bit about these electrowetting effect. So just look at the pure physics behind it. If you have a drop of water and you put it on a metal plate and there's a thin isolating layer in between, then this drop of water will take a certain shape defined via the contact angle between the drop itself and the surface that it's sitting on. And this surface angle, this contact angle, is defined by the surface tensions of all the elements that are involved, which is the liquid, the isolating layer, and the air itself. So the ratios of all those different surface tensions define the shape of this drop. However, if you apply a voltage now between this liquid and the substrate, keep in mind there's this thin isolating layer there. If you now apply a voltage, there will not be a direct current because it's isolated, but the liquid and the metal, they will interact through the electric field that will form. In other words, the liquid is going to try to maximize its surface with the substrate. In the case of water, for example, you can imagine that all the different dipoles in the water are now redirecting, reorienting, and they just seek to minimize or to maximize the surface area with the substrate as indicated here on this picture. Long story short, you can manipulate the shape of this drop by applying and changing a voltage. And this is exactly the concept that Varioptic is using to build liquid lenses. So let's have a look at how they do this. So here you have the sketch of this liquid lens. There's just on the left and right side, there's a window, and there are two liquids inside. For simplicity, we call it water and oil. The key point is they differ in the refractive index. So this surface right here between the two, there's refraction going on. That's, of course, one of the key elements in this design. The other key element is that those two liquids are immiscible, so they don't mix, they don't blend into each other. They're clearly separated, which is why the water and oil example is so great in explaining this. Another detail, those two liquids should also have really the same mass density. If they wouldn't, then the water would just make bloop and the oil would swim on top. And that's certainly not a feature that you want in building a robust lens that you can actually use in the real world. You want to be able to orient it whatever way you want it. So that's that. And the last point here is that the oil should not be conductive. So let's look into how this actually works out. So you have an electrode here, it's indicated with the plus signs, and then you have the water there, and you apply a voltage between this ring electrode over here and your water. And as we've just seen in the example with the drop, again, if you apply high voltages, you're going to create an electric field, and the electric field will push the water towards the electrode. The water will seek to maximize its surface on that ring electrode, which of course also is isolated here as indicated with this thick dark gray line. So as you increase voltage, the water is going to push towards the right in this picture on the top and the bottom, which as a consequence, since everything is sealed off, the oil will push over here in the middle. And again, long story short, you're going to change the radius of curvature of this surface. And all of a sudden you have the ability by, changing a voltage, you are changing the radius of curvature of a surface of two things that have a different refractive index. So that is exactly the feature that you're looking for if you want to have a lens in your hand. And this is exactly how they do it. This is a picture of how this product looks like. You can see the small FPC cable. They call this particular product their A series, and it comes in different clear apertures, fairly small. The latest one they released, I want to say 1 or 2 years back, rather 2 probably, has at least 5.8 millimeters. Everything else is pretty small. So we're going to talk about the implications of those clear aperture sizes in a little bit. But that's how it looks like. But keep in mind, as I said, liquid lens alone doesn't get you far. You have to implement it in an imaging lens, and this is again where Edmund Optics would come into play. So we took a couple of our lenses and we redesigned them. We have a little slit over here in this picture, as you can see. This is where the cable can come out, and then you just put the liquid lens in a holder, put it in there. You can all do this yourself. It's a modular design. You can take the whole thing apart if you wish, or you can just, of course, also get it completely ready to go, plug and play, readily assembled. But that's how you can implement a liquid lens in a fixed focal imaging lens with a C mount, as you know it. Okay, that's of course only the first step of the journey. You're still on your way to a full autofocus system. You still also need a camera. And luckily, both Pixlink and IDS went ahead and implemented the drivers for the Varioptic liquid lenses into their own hardware. So these pictures are IDS cameras, board level cameras, obviously for C and S mount, and you can just take the whatever lens you want to use that has a Corning Varioptic liquid lens inside. You put it on there, and over here in the bottom right corner of those cameras, there's the little socket where you can put in the FPC cable. And of course, IDS also at both Pixlink as well included everything you need on the software side so that you can actually address and talk to that liquid lens and make use of that autofocus feature. So that's quite convenient already. That's all I had so far for the electrowetting and Varioptic technology. Moving things on to the Optitune technology, which is the concept is very quickly described. By contrast, at least. So for Optitune, you have, again, a cell that has a single liquid now. On the one side, the cell is, again, sealed by a window, of course. But on the other side, it has a flexible membrane, very thin membrane. And there is a ring that is pushing on this membrane, and this ring is driven by a voice coil actuator. So you apply a certain current, and this current is then pushing the ring. The ring is pushing on the membrane, and if the ring is pushing harder on the membrane, it pushes all the liquid inside. It pushes all the liquid in the middle of that cell. And yeah, then you get a result, yeah, as it is indicated here in this animated little GIF. So again, this time you have a liquid and air, so two different substances with a different index of refraction. And as a consequence of changing the current, you're changing the radius of curvature and you have a liquid lens. So that's the concept of the Optitune product. And again, this product, they have products that come in different flavors. Of course, they have OEM versions, which is really just the liquid lens and the FPC cable. But they also went one step ahead and they did a little bit more of an integrated product. So this liquid lens comes in a ready-to-use C-mount package that you can either use between the camera and the lens. You just put it in between, or you get an adapter and you put this in front of a normal imaging lens using its filter thread. There's of course some details to be discussed up front in order to avoid vignetting. So in order to avoid getting dark corners, the light must still be able to pass through if you put such an element, such a new liquid lens element up front on an imaging lens. Can't use it with wide angle lenses or large sensor sizes. You gotta be a bit careful there. Except, of course, you don't care about the vignetting. But it's quite convenient, especially if you want to get in there and try things out quickly. It's quite convenient. In terms of drivers, you can use a USB driver if you really want to be quick about it. You can also use some Gardasoft products here. They went ahead and included the Optitune drivers. And the latest products of Optitune actually have the drivers already implemented in their C-mount housing. So that's then also quite easy, convenient, and plug and play. If you want to put it between a lens and a camera, of course, you also have to think about a couple of things as you know this game maybe from using spacers. So you are messing around a little bit with the minimum working distance. You improve it if you want to get shorter, but you also change the focal length a little bit, your field of view a little bit, and certainly you're taking your lens out of its comfort zone with respect to the image quality, right? Because the lens wasn't designed to have an additional, let's say, 20 millimeters worth of space and an additional optical element of arbitrary optical power between itself and the image plane. So gotta be careful a bit and watch out what image quality does when you implement that. But again, it's very easy to just get in there and try things out. Quite convenient. Okay, so now I presented you two different technologies, all with the same goal, and the rest of the presentation will just discuss commonalities and differences of those two approaches. A few things, quite a lot of things they actually have in common, right? The first one is speed. Yeah, that's one of the first questions that comes to mind. You're building an autofocus system. The first question is, how fast can I focus from one working distance to another? And the answer in both cases is a few tens of milliseconds is most likely what you have to calculate with. Of course, it depends on the details. How big is the liquid lens? How big is its clear aperture? How far do you tune the optical power? Is it just a small step? Is it a big step? Either way, if you drive your liquid lens, there's going to be some ripple effect. Then you will have to spend a couple of milliseconds until that rings off and you get into a new robust state. But it can also be single-digit milliseconds if it's just small steps and small liquid lenses. Worst case, you're talking about, let's say, 30 milliseconds roundabout. Second point, hysteresis. Once you change it and you want to go back, is it the same? To be honest, yeah, it's pretty good. And this is again true for both products. I've never run into a problem on that. I was never part of a project where hysteresis would have been a problem. And the same goes for gravity. Although I will add that gravity for the bigger liquid lenses has an effect that you can see depending on how you orientate it. If you orientate it horizontally, so the gravity pulls on it symmetrically, it's of course better in terms of image quality. If you put it vertically, you will see an effect on your image quality, especially for bigger liquid lenses. I didn't touch on this yet, but the Optitune liquid lenses have the ability to create far bigger clear apertures of, say, 10 or 16 millimeters, which is far bigger than the varioptic ones. So effects like gravity are actually more pronounced with the Optitune product because of this, because they are bigger. At the same time, I will say that Optitune did a fabulous job of describing the quantitative impact of that of this effect. So it's really worth to read their data sheets. They have done a beautiful studies there, and it's all there. You cannot just read what it will do to your wavefront. Next bullet would be vibration and shock, and this is also quite surprising, but these products are all very robust. They withstand lots of shocks with ease. They don't break. Is it beneficial for image quality? Probably not, but they are very robust products. And with vibration, yeah, okay, this could of course be a problem depending on what you do. They will not break, but of course it can have an impact on image quality. So you will have to have an open eye and test whether it survives in your application. I will say though that, you know, there's already millions of those out there in the market in the machine vision world, and I doubt that there's, you know, those systems are not run in lab requirements. So also for vibration, really quite robust, those instruments. And talking about this in the same ballpark is the question of what about the lifetime, and you can really just do millions and billions of cycles with those, which is why they are far superior with if you compare them with any motorized solution. They're also far superior to the slow F number approach that I said. You could also just say use a lens at f/16, and all of a sudden you have all the depth of field you could have ever asked for, but you will be, yeah, limited with respect to the diffraction limit that will drive down your MTF, sorry, image quality. And also, of course, you will be limited in terms of your speed, the speed of your process, right? Because you will have to have higher exposure times, because maybe you can't compensate f/16 with more light and all that kind of jazz. Last point, temperature. And this is a very interesting point and actually also a challenge for both. I think there's actually a slide on that coming up right now. Temperature is a big topic here, I think. Let's start, and there's also a little bit of a difference there. The varioptic products, they don't have any self-heating, right? They have this capacitor-like structure, so they don't really draw current, and that's why they also don't heat themselves up. And this is in contrast to the Optitune products. Yeah? As I said, they have a voice coil actuator. You got to apply some current there. They draw power, they heat up. So even if you imagine a perfectly stable thermal environment, varioptic ones would probably already run stable and everything's nice. But where do you have that, right? So as soon as the temperature of the environment changes, also the varioptic products will have to deal with that. And unfortunately, everything kind of depends on the temperature. Yeah? The liquid lens, its index of refraction. And so you will see a thermal shift very quickly with all liquid lenses as soon as the temperature changes, whether that's the environment or with Optitune, they even heat themselves up during operation. They need a couple of minutes until they are there, which is also why Optitune from the beginning provided thermistors in their lenses, which by now also Varioptic has. So now you can measure the temperature at the liquid lens, and then you can calibrate it essentially. Yeah, you have a lookup table stored somewhere, you access that, you measure the temperature, and then you can correct it. But it is a topic to keep in mind. So you can have a very good control over it, but you need to do the effort, you need to have the expertise to be able to do that on the electronic side. And that's why it's quite an interesting topic. All right, continuing with the differences, this was somewhat of a difference, but not really. But I've already touched on a bunch of those, right? So Optitune comes in way larger apertures, up to 16 millimeter. They're current driven, they draw power, whereas this Varioptic, they are quite small in terms of their clear aperture. And they require quite large voltages. So depending on what you want to do, and what kind of safety guidelines you may have to obey, this might cause some extra effort for you. Typically, you will operate this at 45 to 60 volts. I think maximum is like 70 volts, somewhere around this. But again, they don't draw any power, which makes them especially good for mobile applications, because you don't need the battery for them, essentially. So with that, I'm already coming towards the end. Some conclusions, final remarks. Liquid lenses have really quite a success story behind them in the logistics market. The initial example that I made with the conveyor belt and all the packages, and you measure their height, and then the liquid lens jumps around, and you can read the barcode no matter how big the box is. But it's starting to go beyond that market as well. Just a number, yeah, it's already a couple of years old, but as of June 2019, Varioptic announced that they had 2 million of those out in the market, up and running. So that's that. And yeah, things continue, development continues. And yeah, there's a lot of good work that still needs to be done, I guess, to even increase how easy it is to implement this technology. IDS and Pixelink, I already mentioned, they included the drivers on their hardware. They provide some kind of software interface to enable you to talk to this instrument, which is already very nice, but I think we can even go beyond there and make it even easier. And in that context, I'd like to also touch on the OOCI initiative from the EMVA. So that's the European Machine Vision Association. And this is a consortium of lens manufacturers, camera manufacturers, and also the liquid lens manufacturers. And they meet and talk about how to define this interface and how to make life easier for the end user. So I'm looking forward to the outcome of this group. And let's see what they can achieve and how it will affect or improve the user experience for this product altogether. If you care for more additional information, my apologies, I will not be with you to discuss this live and in person, but feel free to reach out to me with LinkedIn and email and everything. I'll provide you my email address on the next slide. If you want to read up onto certain details, I can certainly recommend you to visit the Optitune website and the Varioptic website. In particular, again, I want to highlight, just read a specification document of the Optitune product. It's a great read with lots of valuable detail, and you certainly learn a lot. If you just open one of those, you can download them simply. If not, we also at Admont have a lot of videos and application notes and articles around this topic, which is certainly also a great point to stop by and look for any additional detail. That is actually the end of the presentation, but I was asked by the organizers to also make you aware that Admont Optics is a great place to work, which it is. I love it here. But of course, this is now all way too much detail. I will also provide the slides to the organizers of the OPD, and I'm hopeful that you will get the slides. If you're interested to work with us, we have also 2 guys at the show. So go and talk to them and visit our website. We have globally 36 job openings. We have 8 jobs open in Europe. And of course, you can find all the details on our website. So please feel free to check it out. And yeah, reach out to Niklas and Oleg, who are there at OPD in Tampere. Sorry again for not being able to make it. I blame the weather. I would have loved to be there. I spent 5 hours at the airport for nothing. I hope I will be there next time. Thank you very much for your understanding and your patience with me. I hope again that you will be able to see this video at some point in time. And with that, I'm out. Thank you.